All right, so let me just give you a little bit of an idea about our schedule. Today we're going to be starting chapter 9, and we're going to be talking about what are called confidence intervals. And um, we'll continue with this next week, next Monday. Once we've completed chapter 9, then I will provide you with another homework assignment and another quiz, which will cover, both of those will cover chapters 8 and 9. Then we'll begin chapter 10, which is the last part of the course on hypothesis testing. And that particular, that will be a couple of weeks. Actually, that'll take us right to the end of the semester where we'll have our next exam. So chapter 10 will have its own quiz and its own homework. All right, so basically we will have 2 more homeworks, 2 more quizzes, and a third test, and then the final exam. That's basically what the plan is for the rest of the semester. But nothing this week in terms of quizzes or homework. I will provide you with the quiz and homework at the earliest next week, at the earliest. I would think homework I will assign later in the week, next week, and the quiz might be probably the Monday after that, after next week, will be the next quiz. All right, so that is what we're planning to do. And today we're going to start chapter 9, but I do want to review a couple concepts from chapter 8 because they're going to be used in chapter 9. All right, so I'm going to share the screen with you, and I'm actually going to use another textbook, which actually does a very good job in this third part of the course called Inference, which includes confidence intervals and hypothesis tests. And I just like the way they do things in this particular textbook. It's my choice to use this. It's the department doesn't use this particular textbook, but I like it. And so I'm going to show you just a couple features of it. Maybe one day they'll actually allow us to use this textbook because I think it's very good for students who are new to statistics. Now, inference itself, statistical inference, I think I like this little drawing here, which kind of tells you the story of it, is the process of drawing conclusions about the entire population based on information in a sample. I think that's a great definition. It's very clear, straightforward, and the picture here tells you exactly how it's done. We have a population, and then we collect the data from the population in a random way, right? That's our goal, is to do random samples. And we create our random sample. And then from the random sample, we measure or count one of those two things. We're going to measure something or count something or answer something. You know, come up with some sort of numbers. And then we do a summary number like a mean or a proportion. And we use that information to tell us something about the entire population. So once we have our sample, we do our measurements, and then we do statistical inference, which is a procedure for taking us from the sample to the population. So it's like a loop. We start with the population, we go and we create our sample, we do something with the sample, and then we say something about the population. All right, and the reason for this is that the population is too large, or we don't have the money or the time to ask everybody or have everybody in the population in our study. So instead of that, we do a sample. So we pull people out of the population, we do our study, and then we say something about the original population. We create this sort of loop. All right, and then there's a couple of other definitions that are good to know. If we want to summarize the data that we collect, if the data, if it's in a population, if it's the entire population, then that summary value, like a mean, is called a parameter. All right, parameter. That's the term we use. if what we're looking at is the population. If what we're looking at, if the data is a sample, is from a sample, then that summary information, like a mean or standard deviation, is called a statistic. All right. So parameter is connected to the population. Statistic is connected to the sample. I typically like to ask that question in the final exam. And just to show you how important this distinction is, when I got my master's degree in statistics, there's typically an exam you take right before you graduate. And it sort of summarizes everything that you've learned. And they tell you nothing about what's going to be in the test. Like, you have no hints, nothing. And on my test, the one I got, they actually had a question about the difference between a parameter and a statistic. So obviously, I knew it off the top of my head because I certainly didn't study that. But that was a question on my test. So, but I'm telling you ahead of time that I like asking questions like this. So just know parameter refers to a population, a statistic refers to a sample. All right. And these, of course, are the symbols that we use. And some of these symbols we're not going to be using in our course. Slope in a regression, they typically use this beta symbol, but we're not using that. Don't worry about that. The mean, of course, if it's a population parameter, the mean is mu, and the sample statistic is x bar. All right, so population parameter for a mean is mu. The sample statistic is x bar. That's for the mean. For the standard deviation, we use sigma. For the population standard deviation, and we use S for the sample standard deviation. And then for proportions, we talked about them last time, we use P for the population parameter, population proportion, and we use P hat, little hat above it, for the sample proportion. By the way, we did talk about correlation earlier in the course. And just for your information, this is the letter rho. It's not a P, it's actually called rho. It's a Greek letter, rho. That stands for the population correlation. Normally, we don't deal with that. And then the sample correlations, what we typically deal with, we use the letter R for correlation. And then that, of course, is what our calculator uses for the sample correlation. All right, so the first four we do use in this course, the last one we don't. All right, any questions about just general information about what we're going to be using? This is important for the rest of the course. Now, what we're going to talk about today is estimating a population parameter. We're going to start with the population parameter P, the population proportion. So we're going to be estimating P using what's called a confidence interval. So we're going to get P hat from our sample, the sample proportion, and then we're going to create an interval of values around that to estimate P, the unknown, typically unknown population proportion. All right, so that's what we're going to do today. We're going to use those symbols for that. Now, it says here best estimate. The sample statistics is considered the best estimate of the true value of the population parameter. However, the problem is variability. You know, if one person in the class does a sample and another person in the class does another sample from the same population, we're going to get different sample statistics. So the question is, which one is correct and which one should we use? Well, since everyone's going to get different answers when they do sampling, then the best thing to do is create these intervals. But we start off with that estimate. And that's what we're going to do today. So we have that at point, and we're going to call it a point estimate. I'll show you in a minute. In our actual textbook, we have that definition of a point estimate. And of course, variability of sample statistics. From sample to sample, our sample statistic will vary. Sample mean, sample proportion. All right, I hope I said it so many times that it's really clear to you. That's what we mean by sampling variability. This book is actually very nice. It's fairly new. It uses brand new data. And I like the data because it uses baseball. It's one of my favorite sports. There are some baseball pitchers with their annual salaries in millions of dollars. So here's Zach Britton, 13 means $13 million. This is 2019 salary. All right, so you get the idea of what it's being used for. This is relatively new data that's in here. And then it shows you, and the whole idea here is that they're trying to show you that if one person does a random sample of 30 major league players and then determines their salaries, and another person does another random sample of 13 players, they would get a different list. Now, there might be some common people between the two lists, but it's a different list than the one that we just saw. All right, so this is sort of an illustration of sampling variability. Right? They try to drive home that point. And then, of course, suppose we did 2,000 samples of size 30, 2,000 of them. All right, we create a dot plot of all these. And what does each of these dots represent? They represent a sample with a mean. All right, a sample mean, X bar. So 2,000 samples of a certain size are done, and then we have each one of those samples has a sample mean, and then we plot each of those sample means. We do 2,000 of them, so there's 2,000 dots here. Right? And then we find the mean of all these sample means. All right, and then we find the standard deviation of all of these sample means. All right. Now they use the word here, standard error. Standard error is the definition for the standard deviation of a sampling distribution. That's what we talked about last time. This is a sampling distribution of sample means. All right. And each one of those has a different sample mean. There's a lot of them, of course, that have the same. That's why these dots are stacked. They have the same or similar sample means. But the standard deviation is called the standard error when we're dealing with sample means, sampling distribution. All right. Everybody understand what we're looking at here? These aren't individual salaries. These are sample means of 30 people, 30 Major League Baseball players. Each one of these dots represents a sample of 30. And then there's 2,000 of these samples that are here. All right. And we're looking at the sampling distribution. This is a distribution of sample means from 2,000 of them, sample means of a certain size, in this case, 30. All right, any questions about that, what we're looking at? So sampling distribution is a distribution of sample statistics, either sample mean or sample proportion. There's other sampling distributions that we could talk about, but in this course, we're keeping it very simple. There's two things we're looking at: sample means, sample proportions, and the distribution of them. If we ran the sampling process over and over again, we would get a distribution of them, and that's what's called the sampling distribution. And a sampling distribution has a mean and has a standard deviation. The sampling distribution standard deviation is called the standard error. All right, again, I'm repeating myself, but I really feel like I have to, all right, because talking online here, you may not be paying attention the first time I say it, maybe you are the second time I say it. Here's a sampling distribution of sample proportions. We could do the same thing. We could have a sample and ask people, how many of you like candidate A? All right, and we count the number of people out of all the, let's say we have 100 people in a sample. We ask how many like candidate A, and 55 of you say yes, 45 say no. So if we were interested in the number that said yes, we would say 55 of you said yes, or 55 out of 100 of you said yes, which is a sampling proportion, which is 0.55, 55 out of 100. And if we ran this sampling process over and over again, each of these dots represents one sample of size 100, let's say. And then we, now the example I gave is not very relevant to this particular one, because obviously 0.55 is not here. But what the important point here is that you end up with a sampling distribution of sample proportions, right? Because all these dots represent a sample of size, whatever. And each one of them is a proportion of that sample then answer a question, maybe of yes or no to a question. All right, so that's another sampling distribution. And those are the only two types we're going to look at. We're going to look at one's for mean, that's for a mean. Right? We're measuring something like money. And here, a proportion where we're just counting people who like something. Okay, that's it. Now, the sampling distribution has a shape. And I think we found out last time that if the original population is normal, we say it again, if the original population is normal, and we're looking at the sampling distribution of sample means, just the means, then any sample size it will do in terms of the sampling distribution being looking normal. The sampling distribution will be normal for any sample size if the population distribution of individuals is normal. In many cases, it is not. All right, money, for example, it's not going to be normal looking. The population of salaries is not going to be normal. Why? Because you have most people sort of on the low side, we should see low, but in the $50,000 to $100,000 in the annual salaries, and then we have people like Warren Buffett and others who make billions every year. So there, it's going to be right skewed for salary. So many times, the population of things like salary are not normal, not bell-shaped. They're going to be skewed, right or left skewed. But we found out if the population is skewed, we do have there's something called the central limit theorem that says that as long as the sample size is large enough, the sampling distribution is going to be approximately normal. We found out that at least 30, typically, this is the rule of thumb that's usually used, the sample size is at least 30 in most cases. We consider the sampling distribution to be normal, even if the population distribution is not. All right. Now, if there's nothing mentioned about the population being normal, we assume that it's not normal. All right, just assume it's not, and we need to make sure we have at least 30 people in our sample. Once again, the standard error is the standard deviation of the sample statistic, either a sample mean or sample proportion. That is the definition of it. Okay. And we also found out something interesting last time. We found out as the sample size increases, the standard error, the standard deviation of the sampling distribution, which is the standard error, actually becomes more narrow. Right? So as we increase the sample size, as it goes up, the distribution of sample statistics becomes tighter, more narrow. All right. Here, for example, here, look at these three sample sizes here. Here's a sample size 50. Here's the distribution. Here's the range of values for the sample proportions. And notice that when we get to 200, the sample size, notice the range gets less, right? More narrow. And it's even more narrow if the sample size is 1,000. Remember, each of these dots represents a sample. So here, each of the dots in this diagram here has a sample of size 1,000. Each of the dots in this diagram has a sample of size 200. Each of the dots in this one has a sample size of 50. All right, so that's a very important thing to remember. As the sample size increases, the distribution of the sample statistics becomes narrower. And that's measured by the standard error becoming smaller. The standard error becomes smaller. All right, everybody clear on that? Again, I want to make sure that is important. Now, one of the other important things is that we do random sampling. All right, random sampling is very important. If our sampling is not random, non-random, all right, we do some sort of internet poll, and or volunteers come to our sample, all right, and that's not randomly selected, we cannot do inference. We cannot really say something about our population. Whatever results we get really deal strictly with that group. And that's because our results are biased. They're not They're not unbiased, they're biased. They may be biased in a certain direction. So random sampling ensures that we can use probability to come up with confidence intervals and hypothesis tests, the things that we're going to learn about, so that we can make this thing called inference. We can say something about the population. So in the final exam, if they ask you the requirements for doing either confidence intervals or hypothesis tests, always, and you should write this down, always say is one of those criteria. There are other besides this one, obviously, but the one that you should always say is the sample was selected randomly, as long as it says it in the problem. But that's one of the requirements. And if you forget that, you may end up losing a significant point on the final exam just because you forgot to say random sample. So make sure you write that down, that when we do inference, the sampling must be done randomly. Otherwise, we can't do any of this stuff in this course. We just can't do any of it. All right, so that's really clear. I'm hoping I'm making this clear to you, and it will be sad if I grade your final exams and you don't remember to put that there. It'll be just sad for me to see that, because it's telling me that you either didn't write it down or you just didn't remember to review that. That's a sad thing. And I see such a simple question not being answered correctly, because it is a simple question. All right, so anyway, let's get now to our, stop sharing this. Let's get to our PowerPoint for the PowerPoints for the today. And let's go to 9.1. Sorry, share it with you. Share it. Let's do 9.1. Called point estimation. Now, what is point estimate? Point estimate is a single number that represents a population characteristic. For example, the sample mean would be example of a point estimate. We're estimating, for example, if we want to know the average population of a certain age group, the average of the heights of a certain age group of people, we would find a sample. We would do a sample. We would average their heights, and that average, that sample mean, is called a point estimate. There's only two point estimates that we're going to deal with in this point: X bar for the sample mean, and P hat for the sample proportion. That's it. You guys don't have to deal with any other ones in this course, thankfully. All right. So there's not a whole lot to learn. All right, but you need to learn it. That's my I'm sort of pleading with you, learn it, because it's really, there's really not, I mean, obviously when I took statistics at graduate schools, we had tens and hundreds of these things that we had to learn about. So, and we had to do estimates of. Now we use software, obviously, to do a lot of this work, but we had to know quite a bit. This is a beginning course. So in the beginning course, we're only beginning to look at these things. So there's only two types of point estimates. All right, and please don't confuse them. All right, X bar is for a mean, P hat is for a proportion. That's it. That's all you need to know. All right, and in 9.2, which we're going to look at today, we're going to start looking at proportions. That's going to be our main thing. All right. Now, how do we calculate a sample proportion? Well, we count the number of successes in the sample. And when we say success, we're saying something like, all right, there's candidate A. I know I keep repeating the same example over and over again. It's the simplest thing I can think of. We have candidate A versus candidate B and running against each other. And suppose candidate A is the one that we're interested in, as opposed to candidate B. So candidate A is a success, candidate B is a failure. That's just the language that we're using, all right? So the one that we're interested in is the success. The other is the failure, all right? So if we have 100 people, N is 100, and we ask the 100 people, which one do you like? And again, 55 out of the 100 say, I like candidate A, 45 say they like candidate B. Then if we're interested in the proportion, the sample proportion of people who like candidate A would be 55 divided by 100. which is 0.55. If we were interested in the sample proportion of people who like candidate B, it would be 45 divided by 100, which is 0.45. So that's our point estimate of our population proportion, which is typically unknown. We don't know. That's why we do the polling, because we just don't know. All right, any questions about how to calculate this? So in certain word problems, sometimes the sample proportion is given to you, and sometimes it's not. Sometimes they give you the sample size. Well, they'll always give you the sample size in a word problem, but they may not give you the sample proportion. You'll need to calculate it, which means they'll give you the number of successes. All right, and that's it. I just want to let you know that. All right, so this is an example from a previous, here we go. This is the example they were using here. Surveyed, where we were looking at the proportion of college students who check their phone for something other than the time, more than twice during the night. Obviously, this is old, right? People tend to use their phones much more frequently now than in the past. But according to this very old information, 125 of the 734 surveyed said they used their phone more than twice during the night. All right. And if we calculate the sample proportion, it'd be 125 divided by 734, the total number of people that were asked the question. And it's 0.17, or 17% of college students check their phone. All right. Now, this is a random sample. So this is a point estimate of the population proportion. Population proportion is not necessarily 0.17. It's probably some other number, but hopefully it's close to this number here, 0.17. Any questions about how to calculate a sample proportion? All right. All right. Now, here's an example here of a continuous variable, which is in time, right? I'm assuming it's time. It's a number of hours. It's a number of hours spent on academic reading in 1 week by 20 college students. We're assuming in this case that this is a continuous variable as opposed to a counting variable. All right. So number of hours could be decimals. All right. And if we wanted to take the and here's the dot plot. This is what it looks like, the sample data. All right, so most of it's around 12 to 14, but there are numbers below 1, and there's 28. Somebody actually claims that they number of hours spent on academic reading. They spend 28 hours a week on academic reading. Boy, that's a lot. All right. So suppose the point estimate of mu, which is the mean academic reading time, is desired, and we use X bar as the estimate. All right, and we come up with this is our estimate. So we have 20 in our sample, right? And these are the 20. And if we average them, that means we added them all up and divided by 20, we would get our average. Obviously, you all know now that you can put this information into your calculator, right? Make a list in your calculator using the stat features and then look up the mean. That's all you have to do. Look it up instead of having to calculate it. But if you were going to use the formula to calculate it, X bar is equal to the symbol up here is sum of X, which is the sum of all the values in the data set, and we divide it by n, the number of values in the data set. 287.2 is our sum, divided by 20. 14.36 is our mean, sample mean. You could also find the sample median, also, right? Same thing. The idea is to find the middle value. Notice the mean is a little bit larger than the median. All right, so you could figure out both of those using your calculator. Now they can both be estimates of your population mean, right? They could be. However, in your book, they do talk about what's called unbiased estimates. And an unbiased estimate means that it's the estimate where if we found the long-term average of if we repeated the process over and over again, the long-term process of generating these means, the mean is actually unbiased. The median could be unbiased, but the mean is better. So statistically, and I'm not going to test you on this, statistically the mean is a better estimate, or a better point estimate of the population mean than the sample median is. Okay, so just take my word for it. They do, talk a little bit about that in the book, but this is not an advanced course in statistics. The only thing you have to know is that we look for what are called unbiased estimates when we come up with our point estimate. So an unbiased estimate, the best unbiased estimate for a population mean is the sample mean. Okay. Now here they're saying there may be more than one statistic that you could possibly use, estimate the population proportion. Well, suppose we find 3 different statistics where the long-term average is the same for the population, is the same value. In other words, the middle value for all 3 of them is the same. And the question is, which one do we use? We use the one that has the more narrow standard deviation. That's it. But again, this is a technical thing that's really for somebody who's studying statistics as a career. Just know that the sample mean is the best, all right, for the population. So that's really what they're talking about. So we'll skip through this a little bit. This is basically saying the same thing I just said. And let's see if we can come up with anything new here. Here we go. Here's the definition of an unbiased statistic. A statistic whose mean value, which means long-term value, is equal to the value of the population characterized being estimated. A biased statistic is not as unbiased. So we want an unbiased statistic to be our point estimate. That's the whole idea. Now, occasionally I might ask this on the final exam, but I'm not going to ask you more than the idea that the point estimate needs to be unbiased, right? And this is the definition right here. And that's about all that you need to know. All right. Now, it explains here why the sample range cannot be used as a estimate of the population range. It's just the reason why. But generally, I don't test you on that sort of thing. All right. So you can read through it. Also know that the sample proportion is the best unbiased estimate of the population proportion. So X bar is the best unbiased statistic for estimating mu, the population mean, and p hat is the best unbiased estimate used for the population proportion. All right, that's about all you need to know, and just know a little bit about what we mean by unbiased. I talked about that here. All right, in this slide right here. Any questions about that? Again, I don't want to spend too much time on that because it's not something that we're going to be spending a whole lot of time on. All right, and we're certainly not going to be spending time on the variance here. This is the variance formula. Just know, of course, our calculator calculates the variance for us if we have a data set. Right, it will calculate it for you, but they show you here how to do it. And I think the reason they're showing you variance here, they want to know if the sample variance is a unbiased estimate of the population variance. All right, and the answer is it is. All right. Again, not something I will test you on. All right, so that is this first section in chapter 9. And again, this first section, the things that you have to know about is what a point estimate is. Let's go back to it. You have to know this definition, and you have to know the symbols that we use. P hat for the sample proportion, X bar for the sample mean. I showed you that with the other textbook too. And then just know a little bit about what the definition of unbiased means, and that we need an unbiased estimate for a population parameter. All right, so that's it. We'll stop sharing this one, and we'll go right into 9.2. 2. All right. Now I am going to show you one more section here. Let me get to it. Let me see. Let's see. There we go, 9.2. There is a section called 9.5 that I want to briefly mention to you at the end of today's session. Now, one of the things that I always say when we talk about point estimates is that every single person in class, if they did the same type of sampling, from the same population, the same sample size, using the same procedure, you would all get different sample statistics, different sample proportions, different sample means. Now here we're dealing strictly with proportions. So if we were calculating sample proportions, each one of you will probably have a different sample proportion. You might share the same one, but most likely you have different ones. So what do we need? How do we estimate a population proportion if everybody's point estimate's different? Well, the idea is to create an interval of reasonably calculated sample proportions, all right? So we take our sample proportion and we create an interval of values around it. And then we say with some degree of confidence that our population proportion is somewhere in that interval. And that's called a confidence interval. Now, in this section here, they're going to talk about what's called a large sample confidence interval. That's going to estimate. Remember, we're estimating a population proportion in this case. I'll tell you in a little bit, I'm not going to tell you yet, why we mention it to be large sample. All right, there's going to be a criteria that we are going to use for that. All right, so that's the whole idea. We're going to create an interval of values and call it a confidence interval. All right. So here's the definition of a confidence interval: an interval of plausible values for a population characteristic. All right. And we're going to construct it using the point estimate plus some other information. All right. So the point estimate plus some other information is going to give us this interval. And it's very easy to calculate, by the way. I taught this for many years to students. It doesn't even matter what their mathematical background is. Almost everybody gets it. All right, confidence intervals are pretty straightforward. They're easy to calculate. If any of you feel math challenged, this is not a hard thing to do. All right, this is not calculus. It's not rocket science. It's a very basic thing, and I believe anybody who's taking this course can easily calculate. All right. Now, one of the concepts that needs to be understood when you calculate a confidence interval is this concept called a confidence level. We're going to use a certain method to construct this confidence interval. It's a simple method, but it's a method. And picture, everybody in this class, again, using this method for their particular sample. So this is something that's being repeated over and over again for all different samples. And a confidence level is basically the success rate for constructing confidence interval. What's the success rate? Well, a successful confidence interval would actually contain the true population parameter. In other words, if we say, for example, that the range of possible values for the population proportion is between 0.25 and 0.35. Let's say that's the range, the interval for our estimating our population proportions, between 0.25 and 0.35. A successful interval would actually have the true population proportion in it. In other words, the true population proportion is between 0.25 and 0.35. All right, it's in between those two values. Now, some of you will have your own sample proportion, and you'll create, again, using the same procedure, a confidence interval, and it will not contain the true population proportion. But if we repeated this sampling process many, many times, the confidence level is basically the percentage of all those intervals that have been created that actually contain the true population parameter, in this case, a population proportion, right? So it's not a probability. We're not asking, if I say the confidence interval is 95%, right? That the true population proportion is between 0.25 and 0.35. I'm not saying, and this is absolutely false, I am not saying that the probability is 0.95. If I'm saying 95% confidence, I'm not saying the probability is 0.95 or 95%, that the true population proportion is in between 0.25 and 0.35. No, that's not what I'm saying. I'm saying is if I repeated this process over and over again, this sampling process, and I created these confidence intervals for each one of the sample proportions, 95% of those intervals would contain, approximately 95% of those intervals would contain the true population parameter. And I'm hoping, this is what I mean by being confident, I'm hoping that the one that I have, the sample that I have, the proportion that I've created, does have the true population proportion in it. Because either your interval contains it or it doesn't contain it. All right? So 95% confidence is basically the success rate of all the possible samples having the true population parameter inside that interval, or inside those intervals. All right. Now, here is the definition again of a sample proportion. All right. And here, if you remember last time, this is the formula for the standard deviation of the sampling distribution of sample proportions. It's the square root of p, which is our population proportion, times 1 minus p divided by n, the sample size. The square root of that whole fraction is our standard deviation of the sampling distribution of sample proportions. And this is also called the standard error. This is the standard error. So we can say that for large random samples, and again, we'll talk about what large means a little bit later. For large random samples, the sampling distribution of p hat of all the different sample sample proportions that we could list, it's approximately normal for the mean of the population proportions. So the mean of the sampling distribution is equal to the population proportion, and its standard deviation or standard error is equal to this. Now, let's take a look at this thing here. It says when n is large, approximately 95% of all random samples of size n will result in a value of p hat that is within 1.96. And one thing it didn't forgot to say here, and I should add it in here. Let me just click this here. It's within 1.96 of what? Standard errors of the actual value of the population proportion. It's 1.96 times the standard error. So it's just not 1.96. I'm going to type in standard. Type it. There we go. Standard errors. And it's not. Let's move this over a little bit. All right. So 95% of all samples of size n will result in a value of p hat that is within 1.96 standard errors of the actual value of the population. Now, 1.96 times the standard error, this is standard error formula, is equal to what? It's called the margin of error. All right. Now, by the way, this is okay. This whole thing is making me uncomfortable. I'll actually change this here. So I'll change this later. Not letting me do anything here. All right. So this has to be corrected. I'm going to correct it, but this sigma p hat is not equal to 1.96 times the square root here. It's equal to the square root. And this sigma p hat should be replaced with a m, big M, meaning margin of error. So I can see why students get confused when this textbook writes like this. This is a very bad error here on part of the textbook. This whole thing here, the 1.96 times the square root, is called the margin of error. So what we're doing is we're taking p hat and we're adding and subtracting what's called the margin of error. I can tell you that in political polling, if many times they'll give you the result of a political poll, and say, 55% of the people like candidate X. But then they might say, as part, the media might say, and there was a 5% margin of error. So what they mean is that you take your 0.55, your sample proportion, and you add and subtract 0.05, which is the 5% margin of error. And you end up with 0.5 going up to 0.6. So this is very poorly written here, I have to admit. That's why I like that other book better. But that's just my own personal preference. The math department likes this book for some reason. And so this whole thing here is the confidence interval. All right. And the why 1.96? Where did they get that from? Well, let me show you something, because again, I don't like the way the book does this, but I have to teach from the book. I have no choice. That's what we have to do. So what I'm going to do now is share the screen with our calculator. So I'm going to show you where the 1.96 comes from. If you can picture a normal curve, where the area in the middle of the normal curve, in the middle, is 0.95. Right, remember that we're assuming a sampling distribution is normal for a large sample. We haven't said what a large sample means yet. Right? So it's approximately normal sampling distribution. So if the area in the middle is 95%, where is the 1.96 coming from? So let's use our second, the ARS, and get to our list of probability distributions. And if you remember, when we are interested in finding values, when we have areas under the curve for the normal distribution, we use inverse normal. Remember that? Inverse normal tells us the value for a z statistic. If we're assuming a standard normal curve, the value for a z statistic for a certain area to the left of it. All right, so let's see what it looks like again. Remember this? The area represents the area to the left of this z. If we assume the mean is 0, standard deviation is 1. Now let's think about 95% being in the middle. Right? So there's a left tail and there's a right tail. Now if there's 95% in the middle, how much is left underneath the curve? If we have 95% in the middle, can somebody just yell out how much is left?
5%.
5%, absolutely. And if you can picture the area, that 95% being in the middle and 5% left, the left tail and the right tail, that is the left to the left of the 95% and to the right of the 95%, should be equal, right? The area should be equal if it's normal, right? Because it's symmetric. So if it's 5% that's left, wouldn't you agree that half of it is on the left tail and half of it's on the right tail? I want you to picture that in your mind. Picture that in your mind. The left tail has half of 5% and the right tail has the other half. Would you agree with that? Hopefully you all agree with that. So half of 5% is 2.5%. So picture if we're trying to find the z, that is the positive z. Remember, the standard normal has a mean of 0, so we're looking to the right of that. We want to find the z where the 95% is to the left, and then we have that left tail over there also. Wouldn't you agree that the area to the right of that value is 0.025, right? It's 2.5%. It's the right tail. So if the right tail is 2.5%, that means 1 minus 2.5% must be the area to the left of it. Does everybody agree with that? 1 minus 0.025 is the area to the left. Okay? So if we drew the normal curve, we have 95% in the middle. That value of z, which is the right endpoint of that 95% interval, must have 2.5% to its right, and therefore 1 minus 2.5, and then 1 minus 0.025 to its left. So actually, it's 97.5% to its left. It has the 95%, which is in the middle, plus that left tail, which is 2.5%. That's 97.5%. That's what 1 minus 0.025 is equal to. It's equal to 0.975. And if we scroll down and hit enter, there's your 1.96. That's where they're getting 1.96 from. 1.96 is that value of z, where the area to its right is 2.5%. It's half of that 5% that's left over when you have 95% in the middle. Is that hopefully pretty clear? Now, they have drawings of this in the book, but the important point is I want you to imagine this. 95% in the middle, 2.5% on the left, on the right, 2.5% on the left. And therefore, this z here represents the 95% to its left plus the left tail of 2.5%. That's where they got 1.96 from. All right, so I just wanted to show that to you because we are going to be doing things like this when we want to find these values. All right, we're going to be using inverse normal. So let's get back to the book. All right, so the confidence at a 95% confidence interval, which estimates the population proportion, the left endpoint of that interval is this formula here. It's your sample proportion minus 1.96 times the square root of p hat times 1 minus p hat divided by n. And then the right endpoint is p hat plus this. Now, you may be a little confused. You're looking up here and you're saying, there's no p hat in this square root, and yet there's a p hat down here. The reason why we're using p hat down here is because we don't know p. We're estimating it. We don't know the population proportion. The only thing we have is the sample proportion. So we're going to estimate the p with p hat inside this square root formula. So again, I'm going to correct this thing here. This is incorrect. This is very confusing, the way they have it here. I'm going to replace the sigma here with a big letter M, which represents margin of error. So how do we calculate any confidence interval? We add and subtract to the point estimate the margin of error. And the margin of error has two parts to it. Any margin of error has two parts to it. And I want to actually go back to that other textbook in a minute. That's why I like using this other textbook, because it's so much better in explaining this in this textbook. And again, I'm not being critical, but it's stating a fact. It's absolutely true. This other textbook is so much better. So I'm going to actually go to this section here. And here they talk about the margin of error. So to get any confidence interval, we're going to take our point estimate and add and subtract a margin of error. So here's an example here. Percent of Americans saying that a television set is a necessity has dropped dramatically in recent years. In a nationwide survey of 1,484 people, ages 18 and older, living in the US, only 42% say that a TV set is a necessity rather than a luxury. 42%. All right. Now, they happen to say in this study that the margin of error is plus or minus 3 percentage points. So if they give you the margin of error and they ask you for the confidence interval, you simply add and subtract 3% from the 42%. So 42% minus 3% is 39%. 42% plus 3% is 45%. So we can say between 39 and 45%, we are 95% confident. Right now, we're assuming this is a 95% confidence interval that we're looking at here, but it may not be. We may be using another level of confidence. All right, but this is exactly what we're doing. All right, and again, I like this textbook because they start from the fundamentals. What are we adding, subtracting to the point estimate to get our confidence interval? And what we're adding is called the margin of error. And the margin of error gives us allows us to give a range of plausible values for the population parameter. These are a range of possible values, 39% to 45%. This is the range that we're talking about here. All right. So the sample statistic plus or minus the margin of error is the confidence interval, period. All right. So here's another example. If the sample proportion is 0.54 and the margin of error is 0.02, then the confidence interval will go from 0.52 to 0.56. Why? Because the sample statistic of 0.54 minus the margin of error of 0.02 is 0.52. That's the lower end of the interval. 0.54, the point estimate plus the margin of error 0.02 is 0.56. So from 0.52 up to 0.56 is the range of possible plausible values. That's our confidence interval. If the margin of error is larger, we have a wider interval. So 0.54 minus 0.1 is 0.44. 0.54 plus 0.1 is 0.64. So that interval goes from 0.44 to 0.64. It's a wider interval. Okay, everybody clear on that? So a confidence interval for a parameter, remember parameters, in this case, the population proportion, is an interval computed from sample data by a method that will capture the parameter for a specified proportion of all samples, okay, or percentage of all samples. The success rate of this method that we use is known as the confidence level. All right? Now, notice down here, they say the statistic plus or minus 2 times the standard error is the 95% confidence interval. Where do they come up with the 2? Well, 2 is approximately 1.96. I just showed you where the 1.96 came from. In this book here, they're rounding it to 2. But in our course, I would like for you to use 1.96. All right, use 1.96. So the statistic plus or minus 1.96 times the standard error is going to be your confidence interval. So this whole thing here, the 2 times the standard error or 1.96 times the standard error is your margin of error. So the margin of error has 2 components to it. It has the standard error, and it has this other thing here, this other number that we calculated using inverse normal. And this other number here that we use using inverse normal, it is called, and write this down, it's called a critical value. That's the name of it, critical value. So I want you to write down that a margin of error has 2 components that are multiplied. It has a critical value times a standard error. Now, for estimating population proportions, the standard error is that square root we were just looking at. And the inverse normal gives us these gives us the critical value. All right. Inverse normal. Any questions about that? So again, I like this book the way they do it. They do a really, really nice job for a beginning student in understanding this. All right. Any questions? All right. Now, we can find other confidence intervals using other confidence levels besides 95%. For example, if we wanted a 90% confidence interval, go back to our calculator. Let's say we had the same point estimate, but we wanted to calculate at a confidence interval that was that we were 90% confident. 90% confident. Let's go back to the calculator. We know that the standard error will be the same. The point estimate's going to be the same. The only thing that's going to change is that critical value. So how do we find the critical value when the confidence level is 90%? So think about a normal curve again where 90% is in the middle. Can somebody tell me how much area is left underneath the curve if 90% is in the middle?
10%.
10%. How much is on the left tail and the right tail?
It'd be split 5 and 5.
5 and 5. So if we're trying to find the critical value, we always try to find the positive value, all right? There's going to be two critical values for these intervals. There'll be a left endpoint and a right endpoint. We try to find the right endpoint. So if for a 90% confidence interval, if the area on the tail to the right is 5%, what is the area to the left of that? 5%.
95%.
95. So you have to be very careful. If the area in the middle is 90%, the area to the left of the critical value is 95% because it's the area in the middle plus the left tail. Or another way of saying it, it's 1 minus the right tail. So 1 minus the right tail. So that's the way I'm going to write it. I'm going to do it. So I'm going to, again, go to inverse normal to find the critical value. And in this case, I'm going to say 1 minus 0.05 because the area to the right is 5%. And I'm going to scroll down, hit enter. And here is my critical value. If I was going to round it to 3 decimal places, it would be 1.645. Okay. So that's my critical value. Now, the critical value in this case is smaller than it was for the 95% confidence interval, correct? Smaller critical value. If the critical value is smaller, remember the critical value times the standard error gives us a margin of error. So the margin of error is the critical value times the standard error. The standard error hasn't changed. The critical value goes down. The margin of error also goes down, doesn't it? Because a number that's smaller times a constant is going to be smaller. So the margin of error will become smaller, and that means that the confidence interval will become narrower because we're adding and subtracting a smaller number. So this is a rule that you may want to write down. As the level of confidence goes down, the confidence interval becomes more narrow. As the level of confidence goes down, okay, the interval becomes more narrow, which implies, of course, as the level of confidence goes up, which is a good thing, right? We want our level of confidence to go up. The interval becomes wider. Now, I can tell you that it's always better to have a narrower interval than a wider interval. A narrower interval means that we're more likely that our particular interval will contain the true population parameter. All right, more likely that one does. So obviously, we want narrow intervals. Okay. Any questions about that? So remember to write that down. We increase the confidence level, we make the intervals wider. We decrease the confidence level, we make the intervals more narrow. Okay. Again, these are the types of questions I like asking, both on tests and final exams. So that's why I'm giving them to you. I'm telling you this up front. Now, obviously, I didn't have to do that, and you'd have to try to figure it out on your own on the test, but that's not an easy thing to do. All right. So obviously, I'm not going to make your life miserable. Okay. So let's see if this is it. Go back to our textbook. All right. So again, now we know where we got the critical value from, and the critical value changes based on the level of confidence. All right, and it changes. So whatever level of confidence I give you, you now know how to use inverse normal to find the critical value. And that's what you put into this formula here, the critical value. All right. The only reason it says 1.96 is because it's a 95% confidence interval, and that means the area in the middle of the normal curve is 0.95. That's the reason why we're using that. Okay, so hopefully that makes some sense. Okay, let's keep repeating the same thing over and over again here. All right, now here is something very important. For when we're estimating using the point estimate, the sample proportion to estimate the population proportion, this procedure that I just showed you requires us to assume that the sampling distribution of sample proportions is approximately normal. And how do we know it's approximate normal? We have to do these two calculations right here. We have to, first of all, multiply n, our sample size, times p hat, our point estimate. We then multiply our sample size times 1 minus p hat. If both of these numbers from these calculations are at least 10, both of them are at least 10, then we can assume that the sampling distribution is approximately normal, and then we can use the procedure I just showed you. That's what they mean by large samples in this case for estimating population proportions. The large sample is, the n is large enough so that when we multiply times p hat, and when we multiply n times 1 minus p hat, we're going to get at least 10 for both of those calculations. That's what it means. Now, you may ask, well, what if that doesn't happen? What if you don't get at least 10 for both of them? Maybe one of them is less than 10. Then you cannot use the procedure, this procedure right here. This can't be used to create your confidence interval. Now, fortunately, there is a way out, and I'll show you the way out. There's another type of construction that you can create, and it's in section 9.5. I'm going to show it to you. Now, if I don't show it to you, I don't think I'll have time today, but I will show it to you the beginning of the next session on Monday. All right. We're going to look at 9.5. It won't take very long. It takes about 10 minutes to take a look at that. And we're going to be using a special software program that's free on the internet called StatKey that will show you how to do this process without assuming that normal distribution for the sampling distribution. All right. All right. Now, the rest of this is, let's just look at one example here to show you how this whole thing works. Suppose you have a survey of 1,031 adult Americans. All right. Survey was carried out by this Center for Public Policy. The sample was selected in a way that makes it reasonable to regard the sample as representative of adult Americans. Now, if they say it this way, random sample, all right? They say it's reasonable to regard the sample as representative. It means it was done as a simple random sample or stratified random sample. Some type of random sample was done. Now, out of those surveyed, 567 indicated they believe that college education is essential for success. Notice how old this is, 2010, but let's assume it's current. 567 out of the 10,031 who were interviewed said they believe college education is essential for success. That means the rest of them did not believe it, or maybe had no opinion on it. So what is the sample proportion here? It's 567 divided by 1,031. In this case, 55%. or 0.55. That's our sample proportion. They always express a proportion as a decimal, but if when you're talking to people, you could say 55%. It's the same thing. Suppose you wanted to, first of all, create a confidence interval. Now, the first thing you have to check is, is this a random sample? Yes. Good. Number two, can we use the normal distribution to approximate the sampling distribution? Because otherwise, we can't create the confidence interval. Well, we have to do this calculation. Well, n is the sample size, 1,031. P hat is our proportion, sample proportion. We multiply those two numbers, we get 567, well above 10, right? How about n times 1 minus p hat? Well, that's 364. That's well above 10 also. So yes, in this case, we can construct our interval assuming that the sampling distribution is approximately normal. This is how we do it right here. All right. Sample size is large enough. This is what they mean by sample size is large enough. This is a large sample confidence interval to estimate a population proportion. All right, this is an example of it. All right, so we did our test here to make sure we could do it. All right, and then, by the way, there are 3 criteria. All right, this is the first one we have to make sure of. The second criteria, again, random sample. That was number 3. And look at the third requirement. It's actually number 2 here. It says that the sample size is much smaller than 10% of the population size. This is another requirement when we do random, when we want to do inference. We want to make sure that the sample size is no more than 10% of the population size. Well, we know there adult Americans, there's hundreds of millions of adult Americans. 1,031 is obviously much, much smaller than 10% of the adult population. So that criteria was met too. So on a test, on the final exam, for example, if I ask you for the 3 criteria, make sure you do this calculation and make sure you say it's randomly, a random sample, and make sure that you say that the sample is much smaller than 10% of the population size, which it will be in most cases. All right, how do we calculate our confidence interval? Point estimate is 0.55. It is a 95% confidence interval, so we know our critical value is 1.96. And with estimating population proportions, it's very easy. Inside the square root, we just take our point estimate and plug it in. And then plug in the sample size also. Now make sure here, be very careful. Remember the problem. The problem is that the sample size is 1,031. Go back. I've seen these students make this error sometimes. Sometimes they put 567 for n. This is just the number of people who answered the question this particular way. It's not n. N is 1,031. So please don't make the mistake of putting 567 down for n. You put 1,031. That's the sample size. All right. So this square root is our standard error. 1.96 is our critical value. When we multiply these two numbers, we get 0.029. That's our margin of error. 0.55 plus or minus 0.029. And when we subtract 0.029 from 0.55, we get 0.521. When we add it, we get 0.579. This here is one way of writing the 95% confidence interval for P. Now, sometimes they'll write it in saying something like mu is less than this, and then mu is greater than this, using some algebra. But this is one way of writing the confidence interval. This is the 95% confidence interval. And the only way we can use this construction is if we assume normality for the sampling distribution, the sample was random, and the sample size is less than 10% of the population size. Those 3 criteria are met, we can do this. Any questions? And this is all there is to it, creating a confidence interval for estimating a population proportion. And if I told you what's a 90% confidence interval, you would replace the 1.96 with 1.645 and do the same calculation. All right, and I could give you any confidence level and use the same process. All right, any questions? Now there is one little thing at the end here. I know we're running a little bit late, but I want to show you one other thing here at the very end. In research, we have to choose our sample size before we actually do the research. And the question is, how big of a sample do we need? Well, what many people do is they take the margin of error formula and then they do a little bit of algebra and rearrange it so that we solve for n, the sample size. So the margin of error is the critical value times what? Times the standard error. If we rearrange the formula, do a little bit of math, it's n is equal to p, the point estimate, times 1 minus p, times the critical value divided by the margin of error squared. Right? This is all done through algebra. And if we want to find the minimum sample size, we plug in for p and for the margin of error and do this calculation and then round up to the next whole number and we get our minimum sample size. That's the minimum sample size that we need to do our study. So we need to have up front an idea of what is how narrow do we want our interval to be? Well, that's m, right? M is actually the interval is 2 times m, isn't it? When we add and subtract the margin of error, our interval is actually 2 times the margin of error. That's the length of it. So so m here is just the margin of error, and we can do this calculation. Now, one thing that you may want to know, and the book mentions this, is if there's no good estimate for the point for p, because remember the point estimate is not known yet. We don't know what it is if we haven't done the research yet. So unless the problem gives you p, an estimate for p, please use and write this down, 0.5 for p. So if p is not given in the problem to find the minimum sample size, use 0.5 for p. And of course, 1 minus p would also be 0.5. So it would be 0.5 times 0.5 times this thing that's squared. That will give us the minimum sample size. All right. So when I give you homework, I will give you one of these types of problems to do also. Again, not hard to do, but you have to know how to do it before you take a test. So that's why I was going to give you some homework, just to give you some practice. There's examples in the book also. All right, I ran a little bit over, sorry about that, but that is it for today. Any questions about what we're doing? Any questions about today's topic? Okay, so that is it. So again, we'll finish up this what we're talked about in terms of proportions, and then we'll get into finding confidence intervals for the population, estimating a population mean. We'll talk about that on Monday also. So no questions? All right, so have a very nice weekend, and I'll see you next Monday.
Have a good one.
Have a good